Greetings and welcome, friends. We've been talking about applications of vectors, as well as like equilibrium situations and stuff like that, and finding resultant forces. And we also did some work problem stuff like that. But we're on page 517 nonetheless. Here's question 19. It says, find the magnitude and direction, okay, of the resultant of two forces of 250 pounds and 45 pounds. All right, here we go. Let's see if I can draw a picture. So here's the situation. I've got a 25-degree angle and a 250-pound force. All right, so let's say that's it's probably a little more than 25 degrees, but so there's 25 degrees. Oh, I remember this problem because the degrees and the 250, doesn't that look like if my degree symbol was a 0? Yeah. Craziness. And then there's also a 250-degree angle. What? And where's 250 degrees? Which quadrant is that? I think that's all the way third. And this would be like a 45-pound.
Yeah. Congratulations.
So it'd be like. So here's a 250 degrees, and this is a 45-pound force. So here's my basic sketch. Now I want to figure out the resultant force for this situation. I'm going to redraw this as a tip-to-tail sort of situation. All right. So here's my 250. All right, at 25, and then tip-to-tail, it's going to be like this. All right, something like this for my 45-degree or 45-pound force, right? And I know that this one, this entire angle is 25 degrees. And I know that this angle is 250 degrees, right? And the resultant force, what's a good color for that? We'll use green, why not, shall we? Is going to be from the, so here's like my resultant force vector, something like that, okay? All right, so we did have something like that? Okay. So, this is where we're going to have to do some figuring to figure out how this goes. Let's see. So, no, well, if I was doing this by hand, I suppose you could. So 250, 45, resultant force. Let's see, I'm going to have to figure out some of these interior angles of this triangle, I think. Does it work better? Does it? Yeah, if I could find like one of these angles or something, that would be good. But the problem is neither of them are 250 or 25. They're less than those. Let's see. Or should I break this into two separate vectors, maybe? What do you guys think? That might be the better case. Yeah.
What would you do?
Well, what if I break these into their vertical and horizontal components? I think that will be easier. And if I could represent each vector as its own ordered pair, then I could just kind of add them, and that would at least give me the magnitude to start with, right?
Wait, why can't you do Pythag?
Pythag here?
Yeah.
None of these angles are 90-degree angles. So, I mean, I might be able to figure out some tricky maneuver. Oh, guys, aha, I spotted it. All right. This horizontal line is parallel to this horizontal line, correct? Are you ready for this? You ready for this? This is some math coming at you. This is like geometry. This angle here is 25 degrees. This angle here is 25 degrees. How do I know that? That is alternate interior angles theorem. If you have two parallel lines cut by a transversal, the alternate interior angles are congruent. So this angle would be congruent to that. You guys, anybody? No? Actually, this is ready. Are you guys aight with this? Aight? Alternate interior angles theorem? Aight? Yeah? You remember that? Right, right? So this is 25 degrees. Let's see. Let's do some math. All right. So this technique is actually going to require some sort of law of cosines or law of sines when I'm all said and done. This one would be more like for our Pythagoras friends. And maybe I'll outline this both ways. We'll see. But yeah, man, it took me a second to spot that parallel line situation. That's good. I know, I didn't spot it. I was like, what do I do? Now, so here's 180 degrees, right? Correct? Yeah. What is this angle then? How could I find this angle? If this is 180 degrees, the whole thing's 250. What's this pink? So that's 70, right? So 70 degrees is that angle. So if I want the interior angle here, this angle, it's a good thing I've got all these colors, that's going to be 70 minus 25, angle addition postulate, as you just said there. Right, well done, Colin. So what is 70 minus 25? Anyone get that? I think it's 45 degrees. Those jerks! Seriously? 45 pounds, 45 degrees, 250 degrees, 250 pounds? What? Ugh. Have some more unique numbers, my friend. Wow, I'm sorry. I was just very passionate about that. I am. So, all right, let me redraw just this situation. So I've got 45 degrees. I've got 45 and 250. And I want to figure out this dimension here. Right? That's what I want to figure out. This is a side angle side situation, which the only way I know how to do that is with law of cosines. All right? In a moment, I might come back and do this problem the other way as well, just for funsies, or at least outline how to do that. So law of cosines, you might remember, a squared is equal to b squared plus c squared. And you're like, oh, it's Pythagorean theorem. Ready? Minus 2bc times the cosine of a. There. Oh, I remember this. Good stuff. Good stuff. So I'll call this blue length, or the resultant r here. This will be my a distance that I'm looking for, right? So I'm going to plug in what I know, solve for what I don't. So a squared is going to equal 45 squared plus 250 squared minus 2 times 45 times 250. Oh man, I'm going to run out of room, guys. Let's see, here we go. I can always solve this problem. Oh yeah, you might remember this from the good old days of Math 4.
That was so last year.
Yes, it was very much last year, I agree. Let's see, I'm going to give myself a little bit more room there. How about that? Like that? This is how...
You are a mole.
Yeah, this video has been amazing so far. I love it. So, times the cosine, oh, that's even a different color, orange, of A. What A am I referring to? The 45 degree angle. Actually, that you could do on your hand right there. This angle is the angle opposite the side that I'm looking for here, right? So if this was little a, then big A must have been the angle opposite. There we go. So let's do this. So a squared equals, let's see, 45 squared plus 250 squared. That's a big number. Man, if I made that much money a year, that'd be pretty sweet. And then I'll multiply this rest and subtract it. 2 times 45 times 250 times the cosine of 45, which, by the way, cosine 45 is root 2 over 2. I'll accept the decimal for this case, though. So this is 15909.90. That's fine. Subtract those two, square root both sides. I'm going to get A equals, let's see, 64525 minus second answer. Bam. Root both sides. And I get A is equal to 220.4883 pounds. Okay, so this is like law of cosines approach here. And now I would have to find this angle here.
Wait, what did that solve for?
That found me the R magnitude.
Oh, okay.
How could I find this angle here? All right. Well, now that I know this dimension and its opposite, I can then find this angle using its opposite using law of sines. What's law of sines, you ask? I'll tell you. I'm looking for an angle, so it's going to be sine of, let's say, angle B over little b is going to equal sine of angle A over little a, something like that. So let's plug that in. So sine of angle B, that angle that I'm referring to B now all of a sudden is unknown to me. All right, there we go. So I'm going to try to solve for that over little b, that's the 45 pound magnitude, right? Sine of angle A, that's the 45 degree angle. And the little a is this dimension that I just found, 220.4883. So I would get sine of B is equal to, I'd multiply both sides by 45, and I would have, I'm using law of sines for this instead of law of cosines is why. Because it's the one that makes the more sense, because I happen to have a matching pair of angle and side now. Right, so once you have a pair of angle and its side, then you can use law of sines, which is usually a lot easier than law of cosines. So, how would I solve this for B? It's inverse, both sides. It's inverse, both sides. So I'm going to get angle B equals, and I'll have to plug that into a calculator very carefully. So sine inverse of 45 divided by second ants I'm going to do, just because I happen to have that number 220.4 blah 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 still in there, times the sine of 45. What's sine of 45, guys? Root 2 over 2. And I get B is equal to 8.2976 degrees.
So basically, if you don't remember math forward,
Well, just look this stuff up. Don't worry about it. Don't worry about it. I'll show you this side by side on this. Now, if this is 8.2976 degrees, what's that? This angle here. What's that? This angle here. That is not the angle that my resultant is going off at. But my friend Colin, with his angle addition postulate, he'll tell you how to get that. What could I do with that 8.29? Yeah, friend. Right, so this angle here, all right, is going to be 25 minus that. So it looks like, I don't know, where should I put an answer to this problem? I'm going to say, I'm running out of room. What was my magnitude?
220.4 something.
At, and let's see, 25 minus second answer. And I get 16.7024 degrees. All right. So that's using like law of cosines and all that. That is tricky, as you can see. I had to use some like alternate interior angles theorem. I had to use law of cosines. I had to use law of sines. Other way you could have done this, and I might just summarize it for the sake of time. I could have found the horizontal component for this. This would have been, let's see, that would have been cosine of, if this is x and this is y, x would equal the cosine of 25 times 250. Or 250 times the cosine 25. Y would have ended up equaling the 250 times the sine of 25. All right. For the pink one here, the horizontal component, x and y, the pink x would equal, let's see, 45 times the cosine, sorry, of 250 degrees, which, by the way, cosine is negative at 250 degrees, and y would equal 45 times the sine of 250 degrees, all right, in order to find those components. So my blue vector, or its components, all right, would have been, let's see, 250 times cosine 25, that is 226.57, is that right? Yeah, it's 250, not 220, yep, yep. 5/8, I'll call it, comma, 250 times sine 25 is 105.65. All right, so there's the horizontal and vertical components of that vector. The pink vector. And once I have these two vectors, all I have to do is add them together. Using their horizontal and vertical components, adding 4 vectors that are like that is sometimes easier than adding 2 diagonal vectors. All right, so that's why this might be a little easier. 45 times cosine of 250 should be negative, and it is, negative 15.39. And 45 times sine of 250 is also negative because they're both negative in quadrant 3, negative 42.29. So what would I do with these two vectors? Add them up. All right, and my resultant vector, let's see, 226.58 plus or minus 15.39 is 211.19, and 105.65 minus 42.29 is 63.36. That's not a 6. Now, how does that help us? That is neither of the answers that I have. Well, let me tell you that my resultant force has a horizontal and vertical components of that. So theoretically, how could I find my angle and my magnitude? Magnitude I could find by Pythag. So if I do 63.36 squared plus 211.19 squared, root, I get 220.49. Hopefully that's familiar to us. Yeah. And how could I find this angle theta? You could. Or this is a right angle, so I could just actually use tangent. Tan theta is equal to opposite over adjacent, so 63.36 over 211.19. So theta is going to be the tan inverse of that ratio, 63.36 divided by 211.19, close parentheses, and I get, ready for this, 16.699 repeating degrees, or 16.7 degrees. Is that familiar? Is that right? Right, it's not supposed to equal this one, it's supposed to equal 25 minus that one, which is what we had. What? So pick your poison. This is probably the way that's a little easier for you, breaking it up into its horizontal and verticals and just adding them together, thinking of it that way. So, whew, man, that was like 19 minutes explaining that one problem. Whew, nearly. Well, let's take a look at problem 21 real quick. I'll at least set this up. This one's an equilibrium problem. It says a 23-degree Newton force acting at 60 degrees above the horizontal. All right, so 60 degrees, 23 newtons. So there's one vector. and a second 23 Newton force acting at 120 degrees above the horizontal. Above sounds weird in that case. 120 degrees, another 23 Newton force. Bam, like that. Act concurrently on a point. What is the magnitude and direction of a third force that produces equilibrium? So, think about this third force must be some direction like this. Actually, it's probably even greater than both of those. It'd have to counteract both of those pulling in those directions, right? Does that make sense? Agreed so far? So, think about that, right? Let's draw the picture of tip to tail. All right, tip to tail picture, it'd be like this, and then it'd be like this. Something like that. That'd be 23, that'd be 23. And the resultant force would be like this. So if I want a force that's going to create equilibrium, it will have to be the exact opposite of the resultant force. Would that make sense? Right? Because if it's the opposite of the resultant force, it would bring me back to no overall change. Right? So that's what I'd actually be interested in. So that would be the trick is, can I find what's going on here with these? You could, once again, break these up into their horizontal and vertical components, which are actually going to be the same in this case. And those are actually special right triangles. Wow, we could do that pretty quick. This way would be a little bit trickier, again, using some of your horizontal line math. So this is 120. It turns out if this is 60, then this is 60 in this angle because of alternate ints. And then this would be 120 degrees, and this is 60 degrees because of linear pair postulate. Those two add up to a line. And if this is 60 and 60, then these are 120 total, right? So 120, and then I'd have side angle side. I could do law of cosines and do the whole same routine from there. Find the resultant force. The only difference is I would be interested in the opposite or the opposing force to that resultant force, and I could just like take the angle at 180 to it. Okay, so that's that way. This way, let's do it this way. So actually, I'll save these colors here. So 60 degrees to go from this. Let's see. So this would be 30 degrees, 30, 60, 90. Let's see, this is actually going to be 20. It had to be an odd number. This would be 11.5. And this would be 11.5 times the square root of 3. If you remember your special right triangles, or you can use trig for this, whatever you decide to do. This one over here, this would be 11.5. Because this is 60 as well, because this was 120, and adds with 60 to be 180. And this is 30. You guys getting any of this? No? No?
Where's the 11.5?
Yeah, can you explain that 11.5?
Half of 23.
So, and that's...
Cosine of 60 degrees is 1/2. So cosine the adjacent compared to the hypotenuse, it's going to end up being half of 23. Or if you just remember your special right triangles, that would also work. You could also work from the 30-degree angles perspective. Sine of 30 is a half opposite over hypotenuse, so that'd also be a half. Right? Am I getting that right? 11.5? Yeah. Half of 23. And then this one is, where's my mouse at? Did I just lose my mouse? Yeah, my mouse disappeared, guys. Well, yeah, so I can't really record a video anymore with my mouse disappeared. Mouse disappeared. So yeah, you would do this problem where you take those two vectors, add them together, and blah, 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 like that. This video's been long enough. I'm going to wash my hands of this problem. Enjoy, internet friends. Bye-bye.